Hello students, today we will be discussing about kinematics. So what basically kinematics stands for? Kinematics stands for basically the motion. It's a study of motion. So let me just put that here. So kinematics is nothing but the study of motion of objects, right? So when we talk about study of motion, so what does motion stand for in that case? Let me put that here as well. So motion basically represents the change in position of an object. So it's equal to the change in position of an object with time. So this is how it will be defined, motion. Okay, now, so if I say that any object is moving, so when I say any object is moving, that means what? It is in motion. And to study its motion, how exactly it's moving, whether it is moving at a constant velocity, whether it is moving at a constant rate, or it is accelerating or it is decelerating, that is the study which we are going to do, which is known as kinematics, right? Okay. So the basic of it we have already done in the first chapter, that when we understood the difference between a physical quantity, a scalar quantity and a vector quantity. So I'll be elaborating on those points again, just to reiterate. So to start with, first we define what exactly is the distance. So what does distance imply? What exactly does distance? So if I say that I have two given points, let's say the point A and the point B. If I am not given any predefined path, in that case, any object going from the point A to the point B either can take this path or it can take this path, or more generally, it could take the straight line path. Am I right? So we could see that there can be n number of possibilities that are there. So taking that perspective into account, so what exactly does distance mean? As we see, the distance can be covered by n number of possible paths, and the length of all the paths does not necessarily have to be equal. It can be different and it will be different. So if I say distance, so distance is going to be equals to the length of the path covered, right? So when I am saying it's equal to the length of the path covered, obviously it's going to be dependent on the path. But if I am taking the black colored path and going from the point A to the point B, as well as I take the same black colored path in coming from the point B to the point A, the distance is going to remain the same, right? Because it does not depend on direction, it's a scalar quantity. So we'll say that the distance is independent of the direction. So the distance in going from the point A to the point B is going to be the same in coming from the point B to the point A, provided the path taken is the same. Yeah. So for here, what we are going to say that this is path dependent but independent of direction. So it is path dependent, but it will be independent of the direction. It will depend upon which path you are taking, but it will not depend whether you are going from left to right or from right to left. Yeah. So this is how we define the distance. Now, as we already know, since it's a scalar quantity, it's not going to be dependent on the direction. So the direction is immaterial over here. So if I take that forward and say it's analogous quantity which has the same dimensions, mind you, but spelled differently. the name is different as well as it's a vector quantity. So how do we define displacement here? So the displacement, this is going to be defined as the length of the shortest path. Okay? So when I am saying that it is equal to the length of the shortest path, as you can see, there can be only one single shortest path, which is the straight line path. And therefore, there is no ambiguity in the choice of the path. If there is no ambiguity in the choice of the path going from the point A to the point B, so this is basically, there is no ambiguity in the path, so I am not mentioning that, but this does depend on direction. So this is actually a vector quantity. So when I am saying that it does depend on the path, on the direction, that is whether you are going from A to B or coming from B to A, the values of them, the magnitude of them are going to be exactly same, but there is going to be a minus sign associated. That is AB, the displacement AB is going to be equals to minus of displacement BA. Okay? So this is what we call as a displacement. Now if I go further on this, we have defined displacement. Now using this, obviously when the body is starting from rest, when it is starting from rest, it is acquiring some velocity after a particular interval of time. Because it is starting from rest, finally it does have some velocity, so there is some time interval spent as well. So based on that, we define the next thing, which is speed. So what does speed stand for? So speed is defined as the rate of change of distance covered per unit time. So it's equal to the rate of change of distance covered per unit time. So when I am saying it's equal to the rate of change of distance, distance being a scalar quantity, so speed is also a scalar quantity, right? So let me also mention that here. So this is going to be dependent on the path as well. For a given amount of time, for a given distance, if the time taken is more, or for the same time, if the distance covered is different, in that case the speed value is going to be different, right? Now its analogous value, that is what is known as velocity. So what exactly does velocity stand for? Let me explain that. So when we talk about velocity, velocity is going to be defined as the rate of change of displacement, rate of change of displacement with time. So when we say rate of change of displacement with time, what does that mean? It means that it is how the displacement is changing over time, and therefore this is going to be a vector quantity, right? So we have velocity, we have defined speed, we have defined velocity. So one is a scalar, other one is a vector, right? Now, one question I should be asking you, or actually you should be asking me, is that supposing in any particular case, between any two given points, the net speed is non-zero, but the net velocity is zero. So how can that happen? Or you can also put it this way, that between two given points, the net displacement is zero, but the net distance covered is not. How can that be possible? That is possible. For instance, you're starting from here, you're covering a path, and you're coming back to this particular point. So what does this mean? since the initial and the final points are exactly the same, so the net displacement produced of this particular particle is 0. But distance does not depend on direction, it depends on the path. So the path is taking it in this particular fashion. So here it's going to be the circumference of the circle, assuming that it is a circle. So it is going to be equal to the circumference of the circle, right? So this is the reason. So if a body is moving in a circular path, or for that matter, it may not have to, it does not have to move in a circular path. It can go to one direction and come back to the same point. If the initial and the final points are the same, in that case the velocity as well as the displacements are going to be equal. Right? Let's take that further. Now, if I say the next thing is defined as acceleration. So, when the body is starting from rest, after a certain interval of time, it will acquire some velocity, and then finally, it will come back to rest. So, what exactly is the cycle that is happening? Starting from rest, coming back to rest, but in the midway, it did acquire some velocity, right? And therefore, there is a change in its velocity as well. So, it is from 0, it is acquiring something, and then again coming back to 0. So, there is a change in velocity. So, when I say that there is a change in velocity, so the change in velocity is what is defined as acceleration. So, what is acceleration? Acceleration is going to be equals to rate of change of velocity with time. Again, since this depends on velocity, velocity being a vector quantity, so this is also going to be a vector. So we'll say that this is a vector quantity. Fine. Okay. So far so good. Okay, let me just ask you one thing. What is the scalar analog of acceleration? We know that speed is a scalar, velocity is a vector. Both have the same dimensions. Similarly, distance is a scalar, displacement is a vector. Both have the same dimensions, right? So, what should be the analog of acceleration? It should be having the same dimensions as that of acceleration, but it should be a scalar. Any idea? No? Okay, I'll tell you. See, how do you get to acceleration? How exactly is the acceleration produced? That's the fundamental thing. So, if we go to something that you would have studied multiple times, let's say I have a mass m here, I am applying a force on this, as a result this mass starts accelerating, right? So what will we say? We will say that the force divided by the amount of the mass is equal to the acceleration, or the acceleration, amount of acceleration that is produced depends on the force that is applied, right? So this, the acceleration, since it depends on the force and there is a direction associated with it, so the acceleration has to be a vector quantity. It cannot be scalar because scalar quantity does not have a direction with it. So this is the relation of acceleration. Since force does not have a scalar analog, so acceleration also does not have any scalar analog of it, right? Okay. So we have defined to this particular point. Now we need to put these things into expressions. So what we have? Let's say that the body is starting off with an initial velocity u. After a particular interval of time, it acquires a final velocity v. Okay? So this is the initial velocity, this is the final velocity after a particular interval of time. So the initial velocity with which the particle has already started is a constant, it cannot be changed. This is going to be dependent on the time, and t is the time taken as well. Therefore, since there is a change in velocity, so with time there is also going to be an acceleration a, and finally there is going to be some value of displacement produced as well. Okay, so let's try to understand it further. So when we try to talk about acceleration, so what exactly is acceleration? Acceleration is defined as a change in velocity with time. So change in velocity means the final velocity minus the initial velocity. That will be equals to v minus u divided by the time taken t. Okay, so this is the acceleration that we have. Now, if I have to put that into a graphical form, so let's say, how do I do it? Here, if I say that I have velocity, here, if I say that I have the time. Now, if I could say that initial velocity is u, that is when time is 0. After a certain interval of time, the final velocity acquired, let's say after time t, the final velocity acquired is v. Therefore, if I just join this, so this is the graph that I get from v versus t. Okay, so from this graph, if I am required to find out how much is the acceleration, so how do I do it? I can simply say that if I just join here, so effectively I will get this particular value, that is the vertical distance, is going to be equals to v minus u, right? And similarly, this is going to be equals to t. Therefore, the slope of this graph, slope basically means the vertical change in height and divided by the horizontal change. Vertical change is v minus u, horizontal change is t. That gives me the acceleration a. So acceleration a is nothing but, I can simply put this as the slope of vt graph. Okay, so this is equals to the slope of the vt graph. This is the value of the acceleration that we have. Now, if I want to simplify this particular expression, so what will I get? I can simply say that v minus u is going to be equals to a into t, or the final velocity is going to be given by u plus a into t. So this is what is known as the first equation of motion. Okay? So this is what I am doing using a graphical method. I will be deriving these equations again using something that you will be studying later on in mathematics, that is calculus. Okay. I should have erased this. I will be taking the same graph again. Using the same graph, I will now try to find out what exactly is the displacement produced. So let's say, let me draw the graph again. Here it is t. This is v. This is u. So this is what we have, right? Now from this graph, if I want to find out the displacement that's produced. So displacement, dimension, if you look at it, velocity is length per unit time. If you multiply length per unit time with time, that should give you length, which is displacement. Hence, from this particular figure, if I just find out the area under this graph, I should be through with finding out how much is the displacement, right? So how do I find it? As you can see, this is a trapezium. Trapezium with this side v, this side u, and this is the distance between the two sides, that is t. So if you look into it, this is parallel side having a length v, this is another parallel side having a length u. So I can say the displacement s, which is equal to the area, that will be equals to half sum of parallel sides, that is u plus v, into the distance between the parallel sides, that is t. But what is v? V can be written as u plus at, so I can simply say u plus at into the time taken t, right? So I can put this here as half 2u plus at into t, or if I simplify this, so this gives me ut plus half at squared. So this is my second expression that we have. Right? So we have got the expression for the displacement, we have got the expression for the velocity, final velocity in terms of acceleration. Let's now try to see if we can get an expression of velocity in terms of acceleration and displacement, not time. So let me rewrite the expression that we have got. We have got v equals to u plus at, we have got s equals to ut plus half at squared. So if I square up the first expression, so what will I get? I'll get v square. On the right hand side, I'll get u plus at whole square. Right? So if I expand this, let's see what I get. I can get u square plus a square t square plus 2u at. Right? Okay. Now from these two terms, let me take off a factor of 2a. So if I take off a factor of 2a, I'll get u square plus 2a I have taken off. So what I am left with, let me write down this term first. So I'll get ut. Here I have to have a factor of half. So it's going to be half at square. But hey, this is nothing but the displacement. So this is s. So what we get as a result, we'll get v square equals to u square plus 2x. So this is our third equation that we have. Fine? Hopefully it makes sense to this particular point. Now, what I'm going to do, I'm going to pause for some time. Why? Because now I'm going to tell you about differentiation and integration. That's a concept that is slightly off the track, but I need it for my explanation and derivation of the equations using calculus. So let me introduce the concept of differentiation and integration, that is the calculus. Okay. Now in the calculus we have basically two types. One is known as differential and the other one is known as integral. What is the difference? What is the difference that we have? Supposing you are given a particular function fx, right? The function fx has the argument x. We want to know when I change the argument x by a factor, very small factor, let's say dx, how does the function change? So that is represented as change in the function divided by change in its argument. So this is what is known as differentiation or the derivative. So this is known as the derivative of the function f with respect to x. So that is df by dx. If I try to do the same thing for the integration, so integration is just the inverse of differentiation. So what I can do, I can write this as, if I sum up over each small interval, over each small value of df, if I have to sum up, so that is what is known as an infinite summation. So this is given by df of x. So this is what is the integration and this is the differentiation. Okay? Some simple formulae, let me write it down, of differentiation and integration. Which I'll be using basically. So d by dx of x raised to the power n, I guess I had it down before as well. So this is going to be given by nx n minus 1. Whereas when we talk about integration of x raised to the power n dx, this is going to be given by x raised to the power n plus 1 divided by n plus 1. Okay? So this is the subtle difference. Here you are differentiating, so the power is decreasing by a factor of 1. Here when you are integrating, the power is increasing by by a factor of 1. Here the power comes out, here power comes down. This is the basic difference. Just take a note of these two formulae. We'll now be utilizing these two formulae. Okay? Okay. So, let's see. Coming back to the concept of kinematics. If I say that the change in velocity is dv, okay? Instead of v minus u, if I say that the change in velocity is equal to dv and the change in time taking place is dt, so this is how I am going to define acceleration. Okay? Therefore, I can further say dv can be given by a into dt. So dv can be written as a into dt. So now I'm going to integrate it. Acceleration is just a constant, so I can take off. So this becomes dt here. But on what we are integrating, we don't have anything. So what I can simply say, this can be written as v raised to the power 0 dv. On the right hand side, I can say this is equals to a t raised to the power 0 dv. Yeah? So let's now try to integrate this. If I use the formula, I'll get v raised to the power 1 by 1. But hey, we have an initial value of velocity, right? So if I say that initial velocity is u, final velocity is v, initial time taken is 0, final time taken is t. So what I can simply do it here is, this becomes v divided by 1, and you need to substitute the lower and upper limits, and same here. So this becomes t over 1 integrated between 0 and t. So this results into what? Let me write it down here. So we have upper limit minus lower limit. So that gives me, upper limit is v, lower limit is u. On the right hand side, same thing, upper limit minus lower limit. So that gives me this expression. I haven't used any graphical method here, right? Okay. Let's proceed further. Okay, so if we proceed further, I can rewrite this particular expression as v equals to u plus at. Now u is the initial velocity that cannot change. The body has already started with that. A is the acceleration that we assume that there is a constant force that is active. So effectively, I can say that the final velocity can be written as change in displacement divided by time dt. So this can be given by q plus a into t, right? So if I just do a cross multiplication by dt, so I can say ds, this becomes u dt plus at dt. Yeah? Again, if I have to integrate this, so if I say I start off with 0 displacement, final displacement is s. Here, we say that start from 0 to t, again 0 to t. Now how to proceed further on here? There is no value like we did previously, so we'll simply say that this is 0 to s, and this becomes s raised to the power 0 ds. On the right hand side, u can be taken off, so we can say 0 to t, t raised to the power 0 dt, plus acceleration goes out, we get 0 to t, t dt. Right? Now let's try to integrate and see what we get. So if I integrate this, what are we left with? We'll be left with s by s raised to the power 1 by 1 integrated between 0 to s. On the right hand side, I'll get u. Here I'll get t by 1 integrated between 0 to t. Here I already have a factor of t. So I'll get a into t raised to the power 2 by 2 integrated between 0 and t. Right? Therefore, what will we get? This can be simplified and we will get S equals to ut plus half at square. So this is our second equation which we had derived, if you remember. Right? Okay. Now, we'll go back to the first expression that we had of acceleration. So we said that acceleration A can be given by the change in velocity divided by the time taken. Now, if I just do a means I just do a multiplication division by a factor of displacement. So I can simply say that this will be equals to dV by ds into ds by dt. Right? But what is ds by dt? That is nothing but the velocity. So acceleration can be given by v into dv divided by ds. Right? Or if you just do a cross multiplication, I can simply say v dv is equals to a ds. Clear? So if I say this, then what we get, I can just now put up the integration. So integration of v dv. On the right hand side, it's integration ds. Here I say I am integrating from initial velocity u to final velocity v. Therefore, here as well I can simply say that a into integration of s raised to the power 0 ds. S is being integrated from 0 to s. So therefore, what will we get? If we integrate this, we'll get v square over 2 here, integrated from u to v. On the right hand side, I get a into s integrated from 0 to s. Right? So this gives me what? So this gives me v square over 2 minus u square over 2, that's equals to as, or v square minus u square, that's equals to 2as. Right? So these derivations are from a completely different perspective as compared to what we had done before. Right? So this tells us that these are the three equations that you have. V equals to u plus at, s equals to ut plus half at square, v square equals to u square plus 2s. Right? So these are the three equations that we have. So we'll now, what we are going to do, we'll now elaborate this for other dimensions. First, we'll discuss about how we can apply these for motion in one dimension. Then we are going to expand this to motion in 3 dimensions. So these, in the case of 3 dimensions, these set of 3 equations are going to be thrice repeated. Okay, so effectively for 3 dimensions there are going to be 9 equations. Right? Hopefully you understood whatever we discussed. On that note, let me end it here.